Hey everybody, Dr. A here, and in this video we're going to explore an example of computing the moment of inertia using the integral formulation. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's get into it.
To compute the moment of inertia about the x-axis. So in this case, the x-axis is along the base here of this shape, and this shape is just a rectangle, okay? It's a rectangle with a height h and a base b, okay? So again, notice that this axis is along the base. This is not a centroidal x-axis. This is just an x-axis along the base of this rectangle. So let's go ahead and get started. The first thing we want to make a note of is it's best to orient our dA slice parallel to the axis that we want to compute I about. So we're going to say orient dA parallel to the x-axis. Okay, so when we do that, here's what I'm going to do. I'm going to draw on the original figure here, and I'm going to say we're going to look at a little dA slice right here. Okay, and that dA slice is going to have a height of dy. That's not d sub y, that is a differential dy. And it's going to have a width of x right here. Okay, so again, if you look back in your notes, that was our suggestion, is orient your dA slices parallel to the axis that you're interested in calculating I about. So so how do we know, again, that this dimension is little dy? Well, again, you're making a differential teeny tiny area with a teeny tiny height of dy, but a width of x. So we're going to say dA is equal to x dy, okay? Now, what is x in this case? Well, this is just a simple rectangle, right? This is a very simple rectangle. And so in our case, we're going to be able to say x is equal to the width of the rectangle, or the base dimension b. Again, it's a simple rectangle, all right? So now we can apply our formulation. I sub x is equal to the integral over the area A of y squared dA, all right? And we know dA, we just established that, so we're going to have this integral still over the area of y squared, okay? And dA is x dy, and of course x is the dimension b, so that's going to be the integral of y squared times b dy. Now, what are my integration limits? Now, we said it's the integral over the area. Yes, this is the whole area, but we have a dimension now, dy. So what are our integration limits? Are they 0 to b? No, our slices are horizontal slices. So because our differential is a dy, we're actually integrating from 0 up to h in this case. So we're going to take the integral from 0 to h here. In fact, to be mathematically proper, we should say 0 to h on this integral form as well, because we already have dy built in here. So now we're going to say I sub x equals, and notice that our be mathematically proper, our variable we're integrating with respect to is already here. We have this variable y, okay? Before I guess I evaluate this, where is y? Y is this variable moment arm, okay? Y is that variable moment arm. So we're ready to integrate this now, and we're going to get b is constant, of course, and we're going to get b times y cubed over 3 evaluated from 0 to h, and so we're going to end up with bh cubed over 3, and that's our final answer. I sub x is bh cubed over 3, where x is a horizontal axis at the rectangle base. And that's it.